Hello! Today I'll be testing the physics of circular motion by rotating an object like this around a string. In terms of the variables that I'll be testing, the independent variable will be the angular velocity, in which I'll be rotating this object, well, multiple objects, because that is the one thing I can really control other than the mass. And in terms of the dependent variable, that will be the centripetal force that I'll be using, since I can't exactly control that. Now, I feel like rotating an object using this camera view is not going to be the best, so let me change that real quick. Whoa, now that's a better camera view. Alright, so for the setup of this lab, it's going to be pretty simple. Technically, you only need one object, but because I am a tryhard, I'll be using 3 different objects. Hold up, let me third one. 3 different objects. And each of these objects have like already a pre-recorded mass, as shown here. And I never opened these, so it's going to be the same mass anyway. Now, along with that, I have already pre-measured the length of the string that I'll be using through this measuring tape. And I measured them to 0.25 meters or 25 centimeters and 0.5 meters or 50 centimeters. And now I also have a timer, really. Timer set at 1 minute so that all I need to do is count how many revolutions that this goes through. And now, let us begin using the deodorant stick. I think I tested this before, so it was best when I used it at 0.25 meters because, yeah, it's easier to rotate. So, I'll start this timer and begin counting the revolutions. 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Oh, come on! Begin. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Oh, come on. Hello again. Thankfully, nothing broke. But just in case, I tied this again really a lot tighter. And thankfully, the measurements are still the same from here to 25 centimeters and 50 centimeters. I will not be testing 50 centimeters anymore, on this one at least, because I am afraid of this falling into my mirror and breaking. Alright, so one thing I want to clarify before I begin is that one rotation is going to be from my head, from here to here again, if that makes sense, for the deodorant at least. Like, yeah. And now I have my timer set at 1 minute, and now I will begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 80. 80. All right. Okay, now I'm going to be doing the toothpaste, but don't worry, I will be doing the deodorant stick another 2 more times just because there might be some errors and such, and so I just wanted to have three trials. There's probably going to be different angular velocities, but that's all right. As long as I can show the relationship between angular velocity and centripetal force, then it's all right. All right, so hopefully this is tight enough. If not, oh well, it might slip. So that's why I'm gonna put it at 0.25 meters because this is more likely to slip than the last one. And so my timer is at 1 minute and I shall begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72. 72 rotations on that one. Now, last but not least, the air freshener bottle. Let's go! And I hope this does not crash into anything because this is 270 grams and I'm not sure if that's going to break anything. Alright, so timer at 1 minute and begin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 6, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 72. Nice. So 72 rotations for that one as well. After a couple of more trials and a lot of number crunching, I finally figured out the centripetal force that I used for each angular velocity in all three objects, as you can see here. Now, you might be wondering, how did I figure out the centripetal force when all I had was the string length and the angular velocity in revolutions per minute? And basically saying, where did I get the information from for these two columns? Well, that came from calculations. The main formula that I used, which is the centripetal force formula, is based off of Newton's second law, which is the force equals mass times acceleration. In this case, since it's centripetal force, there is going to be the same mass since inertial mass doesn't really apply here, and I multiplied it by the centripetal acceleration because it's the centripetal force. Now, in calculating it. For example, in the deodorant stick, I first converted the angular velocity into radians per second because that's the units that we need to use. And then after that, I figured out the centripetal acceleration by multiplying the radius of the circle, which will be the length of the string, times the angular velocity from here squared. And after that, I plugged the final value in to the force formula by just multiplying it by the mass of the object. For the deodorant stick, it's 0.048 kilograms, and that's how I got the final centripetal force. And I did this for all 3 trials for all 3 of my objects, as you can see here. Now, you might be wondering, what does this look like? Well, when I graph the data, here, let me zoom it in so that you can see better. For the x-axis, I use the angular velocity, which is going to be in rates per minute. And then in the y-axis, it's going to be the centripetal force, which is in newtons. And as you can see, this is not linear. As such, I linearized the graph by multiplying the angular velocity, well, not multiplying, sorry, I meant by squaring the angular velocity, as you can see here, which changes the units to rates per minute squared, revolutions per minute squared. And now it's linearized. And I did this for all 3 of the graphs because all of them were initially nonlinear. Now, for the conclusion of this lab, for the percent error, there really isn't any, because the only calculated values that we really put in the data table are the angular velocity, which is in radians per second. I just converted it from revolutions per minute that was in the lab, the centripetal acceleration, and the centripetal force. None of these values have a known value because I wasn't able to record them while in the lab, and as a result, they can only be calculated. So there's no way to calculate a percent error from that. Now, in terms of errors and solutions, I faced a bunch of problems in the lab. For one, the yarn that I used stretched out a lot and got frayed in the edges and such, and it could have led to some inconsistent radius, like an inconsistent radius. For a solution, I would just get stronger rope and less elastic rope, if that makes sense, like less stretchy rope, basically. Along with that, there was an inaccurate measurement of revolutions or rotations. Basically, it's like I wasn't able to figure, since I had to like rely on my eye while looking at the video, I wasn't able to fully record the revolutions properly. As a solution, I could have a clearer mark to determine one revolution or rotation, like a piece of paper behind me that has a mark, and then I could just like figure out how much it is through there, like how many rotations I had through there. And along with that, there was an inconsistent velocity of the object. because at some points I accidentally slowed down, while others I accidentally sped up the velocity and used like different varying forces. For a solution, I could use a motor to power the revolutions or rotations, because that's going to be at a constant velocity. Now, the limitations of this, since I was stuck at home doing this lab. For one, like the biggest problem I had was the equipment, because I wasn't able to use a scale to measure the mass of the objects. I had to essentially rely on the labels, since they gave like a mass in grams. As a result, I wasn't really able to do some of the more fun ones that I wanted to do, like measuring like the centripetal force of a plush toy, or like my perfume bottle. I wasn't able to do that because I couldn't measure the mass, since my scale just did not work. It was too light. Like the objects were too light. Along with that, I could have used I wasn't able to use an accurate timer / stopwatch, because all I had was my phone, and a lot of times I missed when it beeped. Along with that, I wasn't able to use a stronger rope that didn't stretch out, because that was the only type of rope that material that I really had, and it was really stretchy, and I didn't like that. Along with that, there's the issue of space. I barely had enough room in my room, basically, and as a result, I couldn't experiment with a larger radius of yarn. For example, I wanted to use 0.5 meters and maybe even 1 meter, but I was just not able to, based on the size of my room. Along with that, again, like I said earlier, I didn't have enough space to put a sheet behind me or something to properly mark the point for one rotation. And finally, the fact that there's because of COVID, really, I wasn't able to work with a lot other people. Additional people really could have helped with keeping accuracy, since I had to keep track of the stopwatch, count the rotations, as well as keep a constant velocity to the best of my ability on the object, which is very difficult for a single person to do. If I were able to work at this in school, in person, I would have been able to have 2 other people work with me and help me with all the calculations and whatnot. So, yeah, the fact that there wasn't other people was a definite downer. Now, the relationship between the variables. The centripetal force, which is the dependent variable, is directly proportional to the square of the angular velocity, the independent variable. And we saw this in the graphs earlier, where in the original was non-linear, because you had to square the angular velocity in order to make it a linear. As such, that's the relationship between the variables. Now, that concludes my lab. I hope you have a great day and that you enjoyed my lab and the presentation of it. Bye!